Okay, wonderful. Great. Well, first, let me start by thanking the organizers for putting on this really wonderful meeting and for giving me the opportunity to speak. This is my first time visiting Brazil. Oops, still not the right view. And I'm very happy to be here. Sorry. Maybe this thing will just disappear on its own. Okay. Okay, so, geez. Technical difficulties right from the outset. Sorry. This is. It'll disappear. Okay, so today I want to tell you about. Okay, can't see this very well. Electron crystals in 2D materials. So no, it didn't disappear. That's okay. So what is an electron crystal? Well, as the name suggests, it is a crystal composed entirely of electrons, and such electron crystals are expected to arise in otherwise homogeneous systems when Coulomb interactions far exceed the kinetic energy of the electrons in the system. So the idea that this could happen in a metallic system was, of course, first suggested by. Thank you. Just for the point. Okay. Going to be was, of course, first suggested by Eugene Wigner in the 1930s. And so at the time, Wigner was not interested really in anything exotic or even in electronic crystals per se. In the 30s, this was right after the development of the theory of metals as we know it now by Sommerfeld and Bloch and these sorts of people. And despite the early successes of this theory of metals, Wigner was worried that these theories were essentially free electron theories, or at best mean field theories, and so they might be missing something by not taking more seriously the effects of electron-electron interactions and correlations. And so Wigner did what all good physicists are trained to do, is he took an extreme limit in which the electronic interactions dominate over the kinetic energy greatly, and realized that in such a system, the electrons would crystallize simply to minimize their electrostatic potential energy. Okay, and based on this sort of model, he was able to make some predictions about the electronic energy spectra of metals and some other things. But it's worth noting that at the end of one of his papers, he observed, this is, I believe, his second paper on the subject, he made the following observation that certain irregularities, and here he's talking about some features of his model, come in only at those values of Rs for which there is no practical example. So here Rs is a dimensionless parameter that measures the strength of the interaction to the kinetic energy, and Wigner understood that for the sorts of metals that people knew about at the time, one could not really hope to access a regime where the electrons would really crystallize, and of course he was right. But now we can fast forward 90 years, and with the advent of two-dimensional materials, graphene-based systems and transition metal chalcogenide-based 2D materials, what we now know is such systems can, in fact, be pushed into this regime of very strong interactions, and indeed, they do crystallize. Okay, and now we even have photographic evidence. So this is just some selection of some very beautiful STM data that's been taken on some of these 2D electronic crystals across a variety of rather different systems. So this first image is on a graphene system in a large perpendicular magnetic field, so in the quantum Hall regime, where you can see the formation of a triangular lattice electron solid. This is from Ali Yazdani's lab. This is a STM image on a TMD system, molybdenum diselenide, where you can also see the formation of a triangular lattice electron solid, albeit this one is a bit more warped by the disorder in the system, but you can definitely see these short-range crystalline correlations developing. This is yet another type of system. This is in now a Moray system. This is a twisted tungsten diselenide, tungsten disulfide system, where in this case the formation of the electron solid is assisted by the underlying Moray potential. Okay, so these are rather different systems, and across them you can see this tendency towards electron crystal formation. And there's, I think, more or less equally compelling evidence, maybe not STM images yet, but other very compelling measurements that give evidence for electronic crystallization in other multi-layer 2D materials, multi-valley, two-dimensional electron gases, topological systems, where by this I mean systems in which electron crystallization seems to coexist with some kind of quantized Hall effect, and so on. Okay, so not only do these electron crystals exist, they appear to feature quite prominently in the phase diagrams of these 2D materials. So these are the sorts of things that I want to tell you about today. For the purposes of this discussion, I want to consider electronic or Wigner crystallization in the simplest possible situation, and that's a homogeneous two-dimensional electron gas. So the system is simple enough that we can just write down the Hamiltonian and everybody will understand what I mean. This is just a system of electrons with p squared over 2m dispersion interacting by Coulomb forces, and this gives you a good description of the low-density state of a doped semiconductor, where in that case m star is just the band mass, and epsilon is the dielectric constant of the semiconductor environment. And so this Hamiltonian has just one parameter that tunes its ground state properties. That's this, again, RS parameter, which is a dimensionless measure of the strength of Coulomb interactions to the Fermi energy. Okay, and in terms of the material parameters, it has this form, but what I want you to note is the parametric dependence of this RS on the density and on h bar. Okay, so what you'll note is that the RS parameter varies as the density to the -1/2 power. This means that the low density limit is in fact the strongly interacting limit. But another feature of this is that the large RS limit, that is the limit in which the interactions far dominate the kinetic energy, is also in a sense the small h bar limit. That is, it's the semi-classical limit. Okay, so we can immediately deduce the asymptotic behaviors of the system. So when RS tends to 0, that is when the density is high, then what we are dealing with is a degenerate Fermi gas, and this system will exhibit metallic character. So in this regime, some combination of RPA screening and Fermi liquid theory should give a pretty good accounting of the physics. On the other hand, we can take the extreme interaction limit. This is the limit that Wigner took. When we take RS to infinity, this is the dilute limit, and the system in this limit will crystallize to minimize the electrostatic potential energy. We're dealing with a nearly classical electron solid, and it'll have essentially insulating character. So we can summarize this in a zero temperature phase diagram of the two-dimensional electron gas as a function of the density. So as we just discussed, at high density, we have an electron gas, so we have a kind of momentum space picture of the system. On the other hand, at very low density, when the system crystallizes, and in 2 dimensions, it turns out that the lowest energy structure is a triangular lattice, we have a Wigner crystal, and the transition point between these 2 phases has been, its location has been refined now over a few decades, going back to the late 80s, but the transition occurs when this dimensionless RS parameter is roughly 35. Okay, so the precise number is not very important. What's important is that the crystallization occurs when this parameter is very big in comparison to 1. Okay, so what that means is actually there's a very broad regime between RS of order 1, that is when the interactions are of order the Fermi energy, and the freezing point, where really what we're dealing with is some kind of very strongly correlated electronic liquid. Okay, so there are different ways of understanding what one means by strongly correlated. The way that I like to see it, that I think is very visual, is to look at the so-called pair correlation function. So this object, G of R, tells me the probability of finding 2 electrons a distance r apart from one another in the system. So when RS is small, okay, when we're over here and the system is essentially a gas, that's the red curve, and you see it is more or less featureless, and this is because in a gas, the electrons don't really care about one another's positions. On the other hand, if I make RS big and I go into the crystal phase, that's the blue curve, you see that there's sharp peaks that develop in the pair correlation functions, and the positions of these peaks are related to the shells on the triangular lattice. Okay, and now if I sit in this crystal, in the liquid regime when RS is, let's say, 20, that's the black curve, you see it has these pronounced peaks that are very reminiscent of the crystalline phase. So this is one way of understanding that in the liquid you have these very strong local crystalline correlations built in. Okay, so the focus of our discussion today will be in the crystalline phase, but let me just note that there are a number of open questions around this very simple one-dimensional phase diagram. Despite decades of progress, there are still questions that we don't know the answer to. For instance, are there intermediate phases between the crystal and the homogeneous liquid? What is the nature of the magnetism, both in the crystal and in the proximate liquid phase, and so on? Okay, so there are a number of things we'd like to understand, but for today, what we'll focus on are properties of the crystalline phase. In particular, what we will do is try to understand what sorts of interesting quantum mechanical effects are present in this crystal, in particular as we increase the density towards the melting point. And as we'll see, by thinking seriously about these quantum mechanical effects, we'll actually learn something about possible intermediate phases between the crystal and the liquid phase. Okay, good. So let me also note that the things I'll tell you about today are based on some things that have already appeared and have been published. So there's this paper that was done in collaboration with Steve Kivelson's group. And let me highlight Kyung-Soo Kim, who did most of the calculations. He's now a postdoc in Urbana-Champaign. And then these two papers with the group at the University of Wisconsin. And if you find the things I'm going to tell you about interesting, then you can look out for this review article that should hopefully appear sometime in the next few weeks that we wrote in collaboration with Tomasz Smolensky, who's an experimentalist at the University of Basel, and Yo Zhou, who's an experimentalist in Maryland. And a lot of the ideas were developed in collaboration with a large number of my theory friends and experimental colleagues, so I want to acknowledge them as well. Okay, so now let's dive in. I want to start by thinking about the quantum mechanics of an electron crystal, okay? So deep in the crystalline phase, we can imagine a charge density profile that looks something like this. So we have electrons that are well localized to the sites of some kind of triangular lattice, and the localized electronic orbitals have some width that I'm calling xi, which deep in the crystalline phase is going to be much smaller than the inter-electron spacing or the lattice spacing A, okay? So in this regime, the system is highly classical. Now we ask ourselves what happens as we increase the density or decrease this RS parameter. So in this case, we'll of course shrink the lattice constant, but it turns out that you'll also grow the size of these orbitals in such a way that you get into a regime where the electron charge density looks less like this and much more like this, okay? It's quite smeared out, okay? So how can I estimate this width of the localized electronic orbitals? Well, this is nothing but the root mean square fluctuations or the 0-point motion of the electrons about these lattice sites. And if you do some very simple dimensional analysis, you find that the ratio of the orbital width to the lattice spacing goes as this power of Rs, which is just to say that as you decrease Rs, this ratio grows. Okay, and if you do a somewhat more detailed calculation, taking into account the full phonon spectrum of this crystal, what you find is that when Rs is 50, for example, which is well into the crystalline phase and is roughly kind of the lowest densities that can be reached these days in experiment, you find that the ratio of xi, the orbital width to the lattice spacing, is roughly 25%. Okay, so this is to say that the orbital overlap is significant. Okay, so why am I emphasizing this? Well, sorry again about this. I've never had this issue before. So this is important because when you have this kind of significant overlap between the orbitals, you also have significant delocalization of electrons and tunneling, okay? So the electrons sort of lose their individual identity and they start to swim throughout this crystal, okay? And now quantum mechanics comes into play. So what are some of the implications of this sort of electronic delocalization and tunneling? Well, the first thing is that when the electrons can tunnel, they can exchange their positions, okay? So the simplest things you can imagine are two-particle exchanges, but you can also consider larger exchanges, for instance, three-particle exchanges around a triangle and so on. And these exchange processes are very important because they couple the electron's spin degree of freedom, okay? And so this will lead to magnetic phenomena in these electronic Wigner crystals. This is important because it also lifts a massive degeneracy, a 2 to the n-fold spin degeneracy, where n is the number of electrons, that you would have if you had just perfectly localized electrons that could not exchange. Okay, there are other interesting quantum mechanical effects. You can consider, for example, the quantum dynamics of point defects. So here I'm showing you the simplest examples, vacancies and interstitials. So just like the electrons can delocalize through the crystals, so can the defects. And this leads to some interesting phenomena that we'll discuss. And I should note that what I'm telling you about is not novel. These sorts of processes in quantum crystals were well known and studied in solid helium, which is, of course, another very famous quantum crystal. Okay, so let's start with a discussion of these ring exchange sort of processes. So as we said, when the electrons can exchange their positions, that will couple their spins, and you can express that coupling in terms of an effective magnetic spin Hamiltonian, which has the form shown here. So let me walk you through this. This effective magnetic Hamiltonian is a sum over electronic permutations P. Okay, this operator P sigma is a permutation operator now acting on the spin degrees of freedom. Each of these terms has an associated coupling J, And then there's a sign factor -1 to the p. This is the signature of the permutation. So to give you a flavor, I've expanded out the first few terms. So there's a 2-particle exchange, 3-particle around a triangle, 4-particle around a rhombus, and so on and so forth. And each of these spin permutation operators can be written in terms of just ordinary spin operators. So this has some kind of generalized Heisenberg-like form. One important thing that I want you to note is the sign structure here. Okay, so all my J's are, by convention here, taken to be positive. So you see the 2- and 4-particle exchange are antiferromagnetic, whereas the 3-particle exchange is ferromagnetic, comes with a minus sign. And this is actually a rule that's due to Thouless from the 1960s, who showed that when you exchange an even number of electrons, that will lead to an antiferromagnetic coupling, whereas an odd exchange involving an odd number of electrons leads to a ferromagnetic coupling. Okay, so keeping in mind that these exchanges are really due to tunneling processes between electronic configurations related by permutation of electrons, we arrive at this sort of schematic picture of what's going on. So here, this is just the schematic. Here, capital X is an abstract multi-dimensional coordinate in the 2n-dimensional configuration space of the electrons. And what I'm showing you are 2 degenerate minima in this potential energy landscape corresponding to electronic configurations related by permutations of some subset of the electron. So if x0 is some reference configuration of the electrons on the triangular lattice, then px0 is some configuration where I've permuted some of the electrons. And so these exchange processes in this picture are nothing but tunneling events between these 2 degenerate minima. Okay? And the J's, the associated exchange couplings, are just the ordinary tunnel splittings. Okay? So when you've understood then that what we're dealing with is an ordinary kind of tunneling through a barrier problem, albeit in a high multidimensional space, you can immediately guess in a way to approach the problem, which is to apply the familiar methods of WKB theory or instantons to try to estimate these exchange couplings, okay? And this sort of approach should be reasonable at large RS, which, remember, was the kind of semi-classical regime, okay? So in this kind of approximation, these tunnel splittings or exchange couplings take the familiar WKB form. There's a prefactor, h bar omega, where omega is a frequency that's determined by the vibrational frequency in these wells. But the more important dependence is this exponential dependence, e to the minus action over h bar, where the action associated with a particular permutation has this standard kind of tunneling through a barrier form. It's the square root of the mass times the potential barrier height evaluated along the least action path that affects the permutation. Okay? So this is the familiar kind of form for tunneling through a barrier. Good. So what does this actually look like in the case of these ring exchanges of the triangular lattice electron Wigner crystal? So here I've shown just some representative exchange processes, 2, 3, 4, 5, and 6, just the most kind of compact ones. And the semi-classical exchanges associated with these processes have been computed by a number of authors going back now 4 decades to the mid-1980s. So what you find, so actually first so this is just the same formula from the last slide for the exchange coupling, but now I've made the actions dimensionless and packaged all the parametric dependence into this square root of RS prefactor. So this formula tells you, for instance, that indeed when RS is big, when the system is more dilute and more classical, these exchange couplings get smaller and smaller. And then these dimensionless actions have been calculated, again in these references among others. And what you find, so okay, these are just some numbers, but what I want you to note about them is, first of all, they are all kind of order 1 and are all comparable to one another. Okay, that's sort of interesting. It tells you that the tunnel barriers, for example, for a compact 2-particle exchange is comparable to that for a large 6-particle exchange. Okay, so this is due to the very strong correlations in this quantum crystal. But nevertheless, there is a least action, okay, and that's associated with this 3-particle exchange, okay, and that's important. Okay, the fact that the 3-particle exchange is the smallest means that when RS tends to infinity, this is the process that will dominate. And according to this Thouless rule that we just discussed, because this is a permutation involving an odd number of electrons, the ground state will be ferromagnetic as RS tends to infinity. So this is an asymptotically exact statement, okay? It's interesting, it's important because it lifts, again, a massive spin degeneracy. Unfortunately, it's likely irrelevant in practice for any of the kind of two-dimensional electron crystals that we are dealing with at present. The reason is that if you just try to estimate these energy scales, even under the most optimistic conditions, they tend to be small, maybe tens of millikelvin. But the other problem is that, as we noted, these actions are all comparable. Okay, so that means as you decrease Rs away from Rs equals infinity, as you increase the density, these exchange couplings for these various processes will become of comparable magnitude, and so you'll be really dealing with a problem, of frustrated quantum magnetism. And we know in frustrated systems, well, the ground state can be very complicated, and the energy scales tend to get depressed, yet further. So this is interesting, but probably not immediately relevant. So let me tell you then about the other interesting feature of quantum crystals, which is this property of point defects. Okay? Yes, please. Yes, yes. Yes. So you don't fix it, so indeed. So you need to compute, imagine a space-time trajectory where you exchange these two electrons. So you need to find the least action path in this multi-dimensional space. So to get the least action, you want to allow all the other electrons to kind of dance around with it. And that's actually important. So, if you want to get the fact that the three-particle action is the smallest, it is important that you allow all the other electrons to kind of dance in a coordinated way. Indeed. So these numbers come from numerical calculation of just literally minimizing the action with some given boundary conditions, get fixed by the permutation that you're considering. Yeah, exactly. Very good. So, so now let me turn to this other interesting type of process, which is to do with defects. Okay, so again, I'm just showing you cartoons of the simplest types of point defects you can imagine in a triangular lattice electron crystal. So we understand that classically, the creation of a defect in an otherwise pristine crystal costs you some positive energy. But if we now turn on quantum mechanical effects, quantum mechanical tunneling, then we also understand that tunneling will tend to lower the energy of the defect. Okay, so we'll split the classical energy into some sort of defect band whose bandwidth is of order this hopping. There's another interesting feature here that I will not discuss, but I'm happy to talk about if there's interest, which is that the motion of the defect will actually exchange electronic positions and will also lead to magnetic coupling. Okay, so I won't belabor that point, but it's related to these sorts of exchange processes we were just discussing. Good. So this is just a schematic cartoon of what I was just telling you. So this is a schematic plot of the defect energy as a function of the density of the electronic crystal. Okay, so when the density is low, when the system is very classical, it costs you some positive energy to create the defect. And now we increase the density, we increase quantum mechanical effects. The defect energy splits into a band. The bandwidth is of order this hopping. And now you kind of run into an interesting situation where you might encounter the following. So you increase the density, and now, as I've kind of indicated suggestively, the bottom of this defect band can actually drop below zero energy. So what does that mean? So if the bottom of the defect band drops below zero energy, that will trigger sort of self-doping instability, where the system will tend to generate a finite concentration of defects in its ground state. Okay? So yes. Yes. Wait. Sorry, this density is the density of the crystal, not the density of the defects. Sorry, that's yes. 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 I don't think so. I think, these are excited states of the system, but, yeah. So you'll see, maybe the next few slides will address this. So that's the question. Yeah. Exactly, yes, yeah, that's right. So everything will adjust in some self-consistent way. Yeah, so this will all be addressed. Yes, yeah, so you'll see. Good, so if this happens, then, okay, what I'm calling here a defect Wigner crystal would be actually a distinct phase of matter from either the proximate ordinary Wigner crystal or the proximate liquid. It would really be some kind of metallic electron crystal phase. And the idea that such a thing could happen in a quantum crystal is not novel. It goes back to Andreev and Lifshitz in the late 60s. This was the original thinking behind the supersolid phase of helium-4. Okay, so this is not original in the context of quantum crystals, but perhaps original, in the context of electronic systems. Good. So let's ask ourselves, can this happen? Okay, is there such a self-doping instability? And so at large RS, the hoppings of these defects can again be estimated by the sorts of WKB methods I was telling you about for the exchange processes. And so we did that, and we really means Kyung-Soo Kim, who did all the calculations. So we considered these different types of hopping processes, okay? So no need to remember what all of them are, but these are just the sorts of hoppings that we considered, where an interstitial, in this case, can hop around this lattice. And again, I just remind you this semi-classical form for the hopping amplitudes that has this WKB form, okay, where the S's are dimensionless actions associated with a given hopping or tunneling process, and these actions for the different processes are summarized here. Okay, again, the precise numerical values are not important. What I want you to note is that the actions associated with these processes are as much as 2 orders of magnitude smaller than those associated with ring exchanges. Okay, so that means that the barriers to tunneling corresponding to the hopping of a defect are much lower than the barriers associated with exchanges or permutations of electrons in these sorts of ring exchange processes. Okay, okay, very good. So, one can do a similar thing for vacancies. That was done in this paper. I'm not going to show it because that situation ends up being a little bit more technically complicated. The reason is that vacancy defects tend to, they actually spontaneously break a symmetry of the triangular lattice that implies they sort of have an additional orbital index they carry around, so I won't belabor that, but it's qualitatively quite similar. Good. So, armed with these defects hopping amplitudes, we can just write down the band structure of the defects, and we can ask ourselves, what is the energy of a defect as a function of this RS parameter, and can we really trigger this kind of self-doping instability? So this is a plot now of the energy. The red curve is the interstitial energy as a function of RS. Let's just focus on that one, where the energy of the defect is defined in this way. So it's the classical Coulomb energy associated with the creation of a defect. There's some modification of the 0-point energy as well, but the most interesting term is this one, and you can't really see it very well. This is the kinetic energy part, and that's proportional to these hoppings. Okay, so this total energy is what's plotted here, and what we find, at least within the context of these kinds of semi-classical calculations, is that indeed the energy goes to 0 at some reasonably large value of RS, at RS around 70. And this would suggest that indeed, the system can undergo such a self-doping instability where it generates a spontaneous concentration of defects in the ground state. Okay? Sorry, yeah. So the red is interstitials and the blue is vacancies. Yeah, the vacancy story is just more complicated, so I didn't want to talk about it. But in any case, the interstitials go to 0 first. Good. Oops. Nope. Okay. Good. Nope, too far. Right. Sorry, okay, good. So coming from the crystal is this way. Yeah. So just to your point, I think this is probably, so here you're probably a liquid, but I think this is probably also telling you something about the properties of the liquid anyway, but okay. Good. So we can update now our phase diagram that I showed you at the beginning of the talk. So remember, as a function of the density, we had a phase diagram where at large density we have some kind of electronic liquid. At very low density, we have a triangular lattice electron crystal, or Wigner crystal. And what I'm telling you is that there seems to be a possibility that at some relatively large value of RS, there's actually an instability of this ordinary 1 electron per unit cell Wigner crystal towards this kind of metallic electronic crystal phase where you generate a spontaneous concentration of defects, and correspondingly the lattice does not have exactly 1 electron per unit cell. It has actually greater than 1 electron per unit cell, but some general irrational number. Okay, what does that mean for this transition here? Well, the fact that this metallic electron crystal has a lower energy than the ordinary Wigner crystal means that the transition point between these two phases will also be pushed out to higher density, so it'll be less than this RS of 35 that I was telling you before, although that number is harder to estimate. Let me just say that there's a simpler way probably to understand this phase diagram using kind of mean field thinking. Okay, the calculations I've described to you have not those were not mean field calculations, but let me just give you a mean field picture of this to hopefully help with understanding. So in a kind of mean field language, the way we understand this electronic crystal is it's just some periodic potential that is self-consistently generated by the electrons. And so in general, the strength and even periodicity of that mean field potential should be self-consistently determined. So when the system is very dilute, very classical, then you find that that mean field potential does indeed have just one electron per unit cell. And so you have a sort of mean field band structure like the one I've shown you here. And now all I'm telling you is that at intermediate densities, this mean field potential will have an ordering wave vector that does not necessarily correspond to one electron per unit cell. Okay? So in that kind of language, this is not exotic at all. This is just a metallic charge density wave state. But we've approached it coming in from this kind of strong coupling perspective. Good. I don't know yet, but I'm trying, yeah. I think probably not. But it's a really, I think it's an interesting question. Yes, please. Yeah, so the older calculations were biased. Okay, for people who don't know, so these estimates for these critical RS values, these come from quantum Monte Carlo simulations, and indeed those calculations are somewhat biased by the sorts of wave functions they can put in, but I'm trying to help them find this state. And I think and so the earlier calculations would indeed not have been sensitive to these kinds of incommensurate density waves, but I'm hoping with some help they can try to stabilize it. Good, so what is the upshot? So these kinds of quantum mechanical effects appear to be relevant, in particular in the experimentally relevant range of RS. Okay, there's some experimental maybe subtleties with trying to distinguish this kind of defect crystal from an ordinary Wigner crystal, but I have some ideas about that. And one thing that I didn't talk about, but I did mention it, is that these defect hopping process will also mediate a sort of kinetic magnetism, and because these tunneling barriers are smaller for the defect motion, the energy scales associated with the kinetic magnetism will be much higher than those associated with ring exchange, and that could be quite relevant for trying to understand these things experimentally. So I see I'm running out of time, so what I will just advertise, and then I'll end, is that there's an interesting way of trying to enhance these quantum crystalline effects. It turns out that if you just consider a bilayer, okay, so two layers, each of equal density, separated by some distance d, coupled just by Coulomb interactions, then in this system, there are a number of interesting things that can happen. First of all, if you vary the interlayer spacing, or more precisely the ratio of the interlayer spacing to the inter-electron distance, you can realize new Wigner crystal lattice geometries, so that's quite interesting. In the kind of range of intermediate interlayer separations, what you find actually is the crystal can be stabilized to higher density. The reason is simply that you get a sort of commensuration energy from locking the two crystals in the layers that stabilizes the crystal over the liquid. And the implication of that is all these quantum mechanical processes will come with higher energy scales. And probably most interestingly, these bilayer crystals appear to exist. That was demonstrated in experiments from Hung-Koon Park's lab on bilayer molybdenum diselenide now several years ago. So there's good reason to think about these. Let me just flash one thing. So we looked at that problem, again, using this kind of semi-classical framework, and as a function of the interlayer distance, you do indeed find some variety of crystalline structures that can be stabilized, and we looked at the corresponding magnetic orders. So in addition to the kind of ferromagnet that you get at large RS in the single layer limit, and here this is at large layer separation where the lattice configuration will just be two staggered triangular lattices, you get a ferromagnet, but as you decrease the interlayer separation, you get these different geometries, and they come with different sorts of anti-ferromagnetic orders that I won't, maybe I'll, if there's interest, people can ask me about it in the questions, but I'll just skip over this. Okay, and then at finite RS, one deals with more complex magnetic Hamiltonians, and there are yet more phases that emerge and interesting phase transitions. And indeed, we find that at kind of intermediate interlayer separations, the magnetic energy scales can be boosted by as much as 2 orders of magnitude compared to a single layer system. So let me maybe skip this, or I can go through it quickly, I guess. Well, what have we learned? So these electronic Wigner crystals appear to be ubiquitous in 2D materials. For the experimentally relevant range of RS, these are quantum crystals in the sense that I described in the beginning of the talk. In a single layer crystal, point defects have a low barrier to tunneling, and this opens up the possibility of interesting defect liquid or metallic electron crystal states. And in bilayer systems, the situation is yet richer. So let me conclude by combining two seemingly unrelated features of my talk. So I'm visiting you guys from the University of Wisconsin in the US, and so people outside the US probably don't know that we, the state of Wisconsin, are known as the dairy land of the US. So we export a lot of dairy. We are apparently famous for good cheeses and so on. And Eugene Wigner, whose name has featured prominently in this talk, actually spent some years on the faculty at the University of Wisconsin in the 1930s before ultimately going back to Princeton to finish his career. And on his way out, the administration threw Wigner a big party where he was apparently presented with a large wheel of Wisconsin cheese. And Wigner, being the very polite man that he was, wrote a very gracious letter to the administration thanking them for everything they did. And in particular, he included this self-portrait of himself eating a delicious wheel of Wisconsin cheese. And he told the administrators that the cheese was big enough. In fact, it was bigger than I expected. Thank you once more for everything. So let me echo my friend Wigner from Wisconsin, and thank you guys for your attention. I hope the cheese was big enough, so yeah, thank you, and I guess we have some time for questions. Okay.
Thank you, Ilya, for the great talk, and now it's time for questions.
Hi, thanks for the talk. I might have missed this, but so when you introduce or you allow for the system to become self-doping, in what sense are you conserving charge?
So these are all kind of neutral excitations of the system. I mean, I think the simplest way is just to understand it in this kind of mean field picture. Okay, so the system wants to crystallize, but the periodicity of that crystal should be self-consistently determined. Okay, does it, is the periodicity such that you have 1 electron per unit cell or something else? And so, nothing guarantees you that you have to have 1 electron per unit cell. You can have a metallic state where you have some irrational number.
Right. So I guess really what I'm asking is because you made this difference between interstitials and vacancies because they act differently, right? But so in a defect generating process that conserves charge, it would be Frankel pairs.
Well, so if I want to talk about the energy of the defect, then I better always be comparing the energy of a crystal with the same number of particles. So in that sense, it's still a neutral kind of excitation.
I see.
More questions?
Yeah, so very interesting. You showed that these actions for the exchange couplings are kind of very close.
Yes.
But then, when you have the defect, then I would imagine also those get modified near the defect, right? So is there any chance then that the defect gets sort of, more like a polar undressing the magnetism nearby?
Yeah, so in the kind of semi-classical limit, one considers these processes, separately. But really, if you want to determine the magnetic ground state of the system in the presence of the defects and these exchange processes, then you have a complicated problem, magnetic Hamiltonian that you have to diagonalize. And actually, we did that, or Kyung-Soo did that. And the interplay between these exchange processes and the hoppings, does lead to what appears to be the formation of some kind of polarons. So when, so at very large RS, these hopping processes kind of dominate, and that's what, okay, good, will determine the ground state. But as you decrease RS, then, there is some competition between whatever kind of kinetic magnetism is favored by the hopping of the defects and that by the exchange processes, and, okay, then you have to diagonalize some complicated magnetic Hamiltonian. But it does look like you get some kind of partially polarized states, actually. So something that looks like polarons.
Maybe another question is, I mean, if you consider now fluctuations of this state, because you have a Fermi surface that must, coupling to the order parameter, imagine that, there is no pinning or anything, and the order parameter is soft, then, I guess, does the Fermi surface survive, and, does also the Fermi surface then destroy the long-range order of the crystal?
So I think in the most kind of cartoonish picture, really, it's kind of an electron-phonon system again, where now you just have the phonons of the electronic crystal that you're coupled to, And so as Jörg was suggesting, that invites the possibility of a superconducting instability. There could be other instabilities too. That's something we're trying to understand now. Yeah, so I don't know the answer, but I suspect that there should be maybe subsequent instabilities of the system. Yes.
Hi, nice talk. In this intermediate region, in this in real material, perhaps you will find metastable configurations, and do you think some way to dynamically modify the system or self-organize the systems, or I don't know?
So yeah, it's a really good question. I wish I had a good answer. So I mean, so even just in kind of equilibrium, trying to see this state would probably be a little bit tricky. So on the one hand, it would have a periodicity that is different from the ordinary crystal. So if you could measure very precisely the periodicity, that would be one indication. That probably at present cannot be done. Another signature, I think, would be this kind of magnetism. So you know, if I had this ordinary crystal with 1 electron per unit cell, then the magnetism would be governed by these exchange processes with low energies. But if I do have these defects, then the kinetic magnetism should come with some boosted energy scales. So some sort of magnetism would be, I think, a hint
Signature.
that this is
Okay.
relevant. Right, so actually one of the initial motivations for this sort of thing was actually to think about crystals in the presence of actual defects in the system,
Yeah.
and how that would nucleate some of these kinds of defects.
Yes.
So yeah, I would like to understand all those things better at a kind of quantitative level. Yeah.
Okay, okay.
Yeah.
Do we have any more questions?
All right.
Okay, if not, let's thank our speaker again.
Okay, so there's a coffee break now. Let's try to be back at